Piping vibration, periodic flow-induced excitation, understanding vibrations caused by fluctuating fluid flow forces. We'll discuss about dead leg branches, flow over components in fluid stream and thermal wells and its probes. Introduction to periodic flow-induced excitation, overview and significance. Periodic flow-induced excitation is a critical phenomenon in process piping systems that can lead to severe vibration issues and fatigue failures if not properly addressed. Unlike broadband turbulence, this mechanism generates tonal excitation at discrete frequencies, often resulting from vortex shedding or flow instabilities around components. These excitations can lock onto the natural frequencies of the piping or its attachments, creating resonant conditions that amplify vibration levels dramatically. The significance of this phenomenon lies in its ability to cause localized high-stress concentrations, particularly at small-bore connections, thermal wells, and other intrusive elements. In industrial applications such as oil, gas, and chemical plants, periodic flow-induced excitation is frequently encountered in high-velocity gas systems, dead leg branches, and areas with complex flow geometry. Understanding this mechanism is essential for engineers to design robust systems, prevent fatigue failures, and ensure operational safety and reliability. The consequences of neglecting this issue include unplanned shutdowns, costly repairs, and potential safety hazards due to leaks or ruptures. Therefore, proactive identification and mitigation strategies are paramount in modern piping design and maintenance practices. Understanding vortex shedding, mechanism of vortex shedding and Strouhal number. Vortex shedding occurs when fluid flows past a bluff body or obstruction, creating alternating vortices downstream of the object. These vortices are shed at a frequency that depends on the fluid velocity, the characteristic dimension of the object, and the Strouhal number, S, which is a dimensionless parameter representing the relationship between these variables. The shedding frequency can be calculated using the formula F equals S times V/d, where F is the frequency in Hertz, V is the fluid velocity, and d is the characteristic dimension of the component. Strouhal numbers typically range from 0.1 to 1.0 depending on the shape and flow regime. When the vortex shedding frequency coincides with the acoustic or structural natural frequency of the piping system, resonance can occur, leading to significant vibration amplitudes. This lock-on phenomenon is particularly dangerous because it sustains high vibration levels over time, accelerating fatigue damage. Engineers must consider vortex shedding during design, especially for components like thermal wells, probes, and dead leg branches, to avoid resonance conditions. Computational fluid dynamics, CFD, and predictive modeling are often employed to estimate shedding frequencies and assess potential risks. Dead leg branches, tonal excitation and acoustic resonance. Dead leg branches, such as closed relief lines or recycle lines, are common sources of periodic flow-induced excitation in gas systems. When high-velocity flow passes the mouth of a dead leg branch, it can generate a tonal instability similar to blowing across the top of a bottle. This phenomenon creates discrete pressure pulsations that can excite acoustic natural frequencies within the branch. If these acoustic frequencies align with structural natural frequencies of the piping or branch, severe vibration can occur. The generation of vortices at the branch mouth is highly dependent on flow rate, and the worst-case scenario may not correspond to maximum flow conditions. Engineers must evaluate these branches during design and operational assessments, considering factors such as branch length, diameter, and termination type. Mitigation strategies include modifying branch geometry, adding flow spoilers, or installing acoustic dampers to reduce pulsation levels. Failure to address dead leg excitation can result in fatigue cracks at welded joints, leaks, and even catastrophic rupture in extreme cases. This is an example of a dead leg branch. This diagram illustrates the mechanism of periodic flow-induced excitation caused by a dead leg branch in a piping system. The main horizontal pipe carries fluid flow in both directions, as indicated by the blue arrows, while a vertical side branch terminates in a closed end, creating a stagnant zone. When high-velocity fluid passes across the mouth of this dead leg, vortices form at the branch opening due to shear forces and flow separation, as shown by the circular arrow. These vortices shed at discrete frequencies governed by the Strouhal relationship F equals S times V divided by D, where V is the fluid velocity, D is the characteristic dimension of the branch, and S is the Strouhal number. The branch length LLL and diameter DDD are critical because they determine the acoustic natural frequency of the branch, which can interact with the vortex shedding frequency. If these frequencies coincide, a lock-on phenomenon occurs, amplifying pressure pulsations within the branch and transmitting dynamic forces to the main pipe. This resonance can lead to significant vibration, fatigue damage, and eventual failure of small-bore connections or welds. The diagram emphasizes the importance of assessing dead leg geometry and flow conditions to prevent tonal excitation and vibration-induced fatigue in process piping systems. Flow over components in fluid stream, impact of inserted components. Flow over components such as valves, orifice plates, and non-symmetrical fittings can lead to vortex shedding and periodic pressure disturbances. These disturbances interact with the system's acoustic characteristics, potentially amplifying pulsation levels. The Strouhal number for these components varies widely, making it challenging to predict excitation frequencies without detailed analysis. In complex geometries, localized flow separation and recirculation zones can further exacerbate pulsation effects. Engineers should perform detailed assessments using CFD or acoustic simulation tools to identify potential resonance conditions. Design improvements may include streamlining component shapes, adding flow conditioners, or altering piping layouts to minimize flow separation. Failure to manage these effects can cause high vibration levels, leading to fatigue failures at small-bore connections and other stress-sensitive locations. Thermowells and probes, tuning fork effect and design considerations. Thermowells and other probes inserted into the flow stream are particularly susceptible to vortex-induced vibration. When the vortex shedding frequency matches the structural natural frequency of the thermowell, it behaves like a tuning fork, oscillating at high amplitude. This condition can lead to rapid fatigue failure of the thermowell, often within a short operational timeframe. The design of thermowells is typically governed by ANSI/ASME PTC 19.3, but this standard can be non-conservative in certain high-velocity or high-pressure applications. Engineers should verify thermowell designs using advanced analysis methods, considering factors such as unsupported length, diameter, and material properties. Additional mitigation measures include using tapered or stepped thermowell designs, installing velocity collars, or relocating thermowells to areas with lower flow velocities. Failure to address these issues can result in instrument loss, process control problems, and potential safety hazards. Lock-on phenomenon and resonance risk, understanding lock-on. Lock-on occurs when the excitation frequency from vortex shedding or flow instability synchronizes with the structural or acoustic natural frequency of the piping system. This synchronization results in sustained high vibration levels, even if the flow conditions fluctuate slightly. Lock-on is particularly dangerous because it can maintain resonance over extended periods, causing rapid fatigue damage. The risk of lock-on increases in systems with variable flow rates, complex geometries, and insufficient damping. Engineers must ensure that excitation frequencies remain at least plus or minus 20% away from structural and acoustic natural frequencies to avoid resonance. Predictive modeling, experimental modal analysis, and vibration monitoring are essential tools for identifying and mitigating lock-on risks. Design strategies include altering component dimensions, adding supports, and installing damping devices to disrupt resonance conditions. Impact on piping integrity and preventive measures, consequences and mitigation strategies. Periodic flow-induced excitation can lead to severe consequences, including fatigue cracking at welded joints, failure of small-bore connections, and damage to instrumentation. In extreme cases, these failures can cause leaks, environmental hazards, and safety incidents. Preventive measures focus on both design and operational strategies. Design considerations include minimizing dead leg branches, streamlining flow paths, and ensuring thermowell designs meet or exceed industry standards. Operational strategies involve monitoring vibration levels, adjusting flow conditions to avoid resonance, and implementing corrective actions such as installing acoustic dampers or braces. Industry best practices recommend conducting qualitative and quantitative assessments during design and periodically during operation to identify high-risk areas. By adopting these measures, engineers can significantly reduce the likelihood of vibration-induced failures and enhance the reliability of process piping systems.